towards the end we were deriving the kinetic energy equation from the momentum equation. So after taking a dot product with velocity of this, we had derived that the left hand side can be written as del by del t of rho u square by 2 plus del dot u times rho u square by 2 equals u dot f plus u dot del dot t. Okay, so this is our kinetic energy equation, and this I had classified as the rate of mechanical work. Okay, this was classified as the rate of mechanical work in the kinetic energy equation. Okay, so today what we are going to do is use this equation to see what does the temperature equation in fluid mechanics look like. Okay, so basically this is the transport of kinetic energy. We can formulate an equation for transport of total energy, and we know total energy is a sum of kinetic energy and internal energy. So by subtracting this from the total energy equation, we can obtain the internal energy equation, which is what we are going to use to get the temperature equation. Okay, so for total energy equation, we again go back to the physical law that we all know for the total energy. So the law that we know for total energy is our first law of thermodynamics. So the first law of thermodynamics states, what does the first law of thermodynamics state? Huh? Heat plus equals, why change in internal energy? Why change is not in focus, internal energy is in focus. Why do you call it change in internal energy? Why not total energy? Or does it depend on that we are doing, or something very peculiar about your thermodynamics classes which did not require you to consider anything else except for internal energy? So whenever you were discussing about this first law of thermodynamics, unfortunately you had a gas in a piston which was stationary. Okay, so you never bothered about total mechanical force that is acting on the system and any kinetic energy that the system might have. Okay, so you were looking at internal energy only. Actually, in your first law of thermodynamics, what you must account for is the change in total energy is equal to the net work done on the system, the net work done. Okay, this is not necessarily any deformation work or anything else. This is the net work done plus the net heat supplied. Okay, the change in total energy of the system is equal to the net work done on the system and net heat supplied on the system. Now notice I have written this delta over here. This is a notational nuance for thermodynamics because the heat and work are not state variables, they are path variables. So I cannot represent them as complete derivatives. Okay, so that's why I'm using delta. If you don't understand it, it's perfectly fine. What we are going to do is we are going to use the rate form of this equation, which states that dE by dt is actually, so the net rate of change of total energy of the system is equal to the total work done on the system and to, rate of work done on the system and the rate of heat supplied to the system. Okay, and now we can start using the Reynolds transport theorem here. How? E is basically integral over bt of rho times E times dV. Okay, where this E is total specific energy or the intensive quantity corresponding to your total energy, and this E is going to be equal to the internal energy plus your kinetic energy kinetic energy per unit mass. Okay, this E here is basically the total energy of the system. Okay, kinetic plus internal. Notice I have not written any potential energy because I am going to account for that by the work done due to the conservative forces. Okay, we are going to account for that by work done due to conservative forces. So this is your E. Now again, applying the Reynolds transport theorem, we have d by dt of rho E dV, which is going to be equal to del by del T of rho E plus del dot of rho U E. Okay, this is what we have for the left hand side using Reynolds transport theorem. Okay, now let us look at the RHS. Let us look at the RHS. So the first term on the RHS is this guy. So this is the net rate of work done by all the forces on the system. What are the forces? Forces are, you have F and del dot T. Okay, technically what you have to do is you have to consider your fluid blob. So on the surface you have some traction vector T. Okay, and for on a volumetric element you have the force F. Okay, so what you have to write, the way you have to write this as is, this is going to be F dot U dV plus the work done by traction force over the whole surface. So T dot U ds. Okay, so this traction vector we know is equal to, so I can write this as u dot t. You can simplify this using index notation. This is u dot t dot n ds, which using the Gauss divergence theorem I can write as this guy. So the net rate of work done is F dot u dV over bt. Sorry, this will also be bt, and del dot t dot u dV over bt. Okay, this is our net rate of work done on the system. And now we start to see how this appeared in our kinetic energy equation. Okay, basically the net rate of work done per unit volume, if it's going to be this guy, then if you open this up, you are going to get a u dot plus a. So this you can confirm using index notation, this guy, where this double dot is the double dot product. Okay, this means Tij del u I over del xj. Okay, that is what we have for the net rate of work done, where this we have isolated as the rate of mechanical work since it appears in our kinetic energy equation. So this is the rate of mechanical work. So this is the rate of work or power which is resulting in translation of fluid elements. Okay, this is resulting in translation or acceleration, if it's there, of fluid elements. If you look at this guy, this should give you some insight about. So this is what we have. Now we know this gradient of velocity can be broken down into the symmetric and the anti-symmetric part. We know the stress tensor has to be symmetric from conservation of angular momentum. So if stress tensor has to be symmetric, if stress tensor has to be symmetric, then what is this product going to be? Simply T double dot S. Okay. So for T to be for T symmetric, so T into S plus omega is T into S basically. Okay. And now S was our rate of strain or strain rate or rate of deformation. Okay, that is what S had. Omega had rate of rotation, S had rate of deformation. So this is basically T double dot S, stress tensor double dot rate of strain, which is going to give you the rate of deformation work done. So this is rate of deformation work. The intuition is something like this. You have T double dot del U. Okay, so just like I had given you some idea why this is rate of mechanical work done. Basically, let us say you have some force here, some stress here, and some stress here, and these are not equal. As a result of that, there is a net force applying on the center of mass, which is going to translate the body, and you are basically doing that in U dot del dot T. That is the difference in the stresses on the two sides times the velocity of the center of mass. On the other term, what you are doing is you have some stress up acting, either it's equal or not equal, it's not your problem. What you can do is you can take an average on the center of mass, and now what you have to look at is that this side might be traveling at a different speed compared to this side. So there will be net deformation of the fluid element. Okay, so the force on center of mass times that deformation speed, okay, that is giving you the rate of deformation work. Okay, so this quantity is giving you at what rate power is trying to deform locally fluid elements. Okay, now deformation work doesn't have to mean that this is compressive or extension work, as you guys are maybe more familiar with. So this is very obvious. Let us say if you have something like this happening, okay, but there are other works that are possible. For example, you could have a fluid element that is undergoing shear. Okay, that is, let us say, undergoing shear. On a fluid element that is undergoing shear, you could have the rate of deformation work as well. Okay, and there is a problem on in the kinematic sheet on this. We have to show how does a square fluid element deform as it moves ahead in a boundary layer. So you can do that visualization and then think about what does this S, what this S would be for for a general flow, not a very general flow, but at least let's say in a boundary layer what this S would look like, or in different types of flows what this S could look like, and that will give you an intuition what this T could look like, or rather T double dot S could look like. Okay, so this is your rate of deformation work. Now about this is all what we have to say about del W by del T. Now let us look at del Q by del T. So this del Q by del T is the net rate of heat supplied or heat added to the system. Okay, so there could be some influx of heat from the surfaces. Let us denote that with a Q vector. Okay, this is the flux of heat inside the fluid element from the surface. Let us call it as Q. So this becomes Q dot N. So if Q dot N, so if Q dot N is like this, you have N that is opposite. Q is taken as positive when it is going inside the inside the fluid element. So this basically means it has to be with a minus sign like this. So this is the net rate of heat supplied through the surroundings, from the surroundings through the surface of the fluid element, and then there might be some volumetric heating which we write as S dot here. Okay, and now again you can see here I can apply my Gauss divergence theorem, and my del Q by del T will simplify to be minus del dot. Okay, now I have all the terms. So this was my LHS. this was my RHS of work done, rate of work done, and this is the RHS of rate of heat supplied. All of these terms are in volumetric integral. So I can take inside, use the same logic that there is an integrand, okay. There is an integral which is 0 for an arbitrary body, so the integrand has to be 0, okay. And that gives us the statement of first law of thermodynamics for a fluid element, that is del by del T of rho e plus del dot of rho u e equals minus del dot q plus s dot plus del dot of t dot q, where this E is again u square by 2 plus EI, which is the internal energy, specific internal energy. So can you explain how you wrote del Q by del T down? Which part? This. Which one? This one or this one? So there is a flux of heat that I'm defining. Okay, this is something that I'm defining. I'm not asking you to know it from somewhere. It is something that I'm postulating, that there is an influx of heat. Okay, basically this means what is the total rate of heat added per unit surface area from the surface, and I'm just integrating that with the surface area. Okay, and then the second one is like volumetric heating. So volumetric heating you could consider as, so think of let's say think of a chamber which has hydrogen and oxygen and you are igniting it. There's no heat that so let's say everything is at the ignition temperature, there's no heat that is going to be added to from the surroundings due to simply chemical reactions which are exothermic in nature. There might be heat addition to the fluid. Okay, that is what volumetric mixing means, that due to chemical reactions or some other thing there is some heat added in the volume which is not coming from the surfaces. Okay. Oh, this is, so I have not put double line, so this is not the strain rate, this is just. So what do we call it? What do we call what? So that is energy generated per unit volume. Yeah, this is not energy generated, I would call heat added per unit volume. So if it is a filament, let's say if it's a filament that is heating up, let's say you have something like this in a fluid, then this filament surface is forming the surface of the surface of the fluid elements, right? So technically you can model it as both depending on how much details you want in your fluid solution. If you are not interested in how is the flow going to convect due to the heating of the filament, if you're not interested in that, then you could model it simply as a source term, part of the system, calling it S dot. Okay, but if you are interested in the details of how the flow is going to convect as a result of the non-uniformity of temperature of the air or whatever fluid is there, then you cannot model it as a volumetric heating. You will have to solve for fluid flow in the domain where fluid is, and then wherever fluid is not, that is the surface of that domain, right? So then it will be a heat added, flux added through the surface. Okay, that's a very good question, and that highlights of how these two might be interchanged depending on what kind of details you want from your modeling. Okay. In this course, most of the times we are not going to do the first one, which is called the lumped modeling. That is a more mechanical uh, way or approach of analyzing systems. Okay, we are going to look at the details of how the flow might happen. So when we, as we move forward, we will try to look at a what is known as a convective boundary layer. So let us say you have a heated plate. Okay, this plate is at temperature T and surroundings are at temperature T infinity. There is gravity in the system. We will formulate the equations for a natural convection boundary layer in this. Okay, we will formulate these equations. We'll show that you can solve them somehow. Okay, and in this basically what we are interested in is you are interested in solving the details of the flow due to external heating. Okay. Yeah. So negative sign is because my convention of Q is that Q is going to be defined when it is going inside the body. Okay, that is what my convention of Q is. I am taking that convention, that is not coming from any physical picture. I am taking that convention that Q is Q is a vector anyways. It's Q is vector and it is, let's say, oriented along when it is inside the body. So when heat is coming inside the body, that's how I'm defining Q. Q dot n by definition of n, which is the outward normal, will be negative in that case. So to compensate for that negative, I have taken a negative sign, because when heat is adding, I want this quantity to be positive. All of this is convention. Okay, you'll see I'll just negate that negative sign again by defining. So this Q, so defining Q is same as defining T. Okay, the way heat is flowing inside your fluid element is actually the same as whatever traction vectors would be acting on the fluid element. Why would there be any traction? Let's say there's, you isolate a fluid element in the same fluid. Let's say this is air and you isolate a small blob of air inside this room. By what physical picture do you expect some traction vector on that isolated blob of air? Okay, let's say there's some pressure of air. You said viscosity. Okay, all of these are due to what? When you are zooming in inside the fluid, what is the physical mechanism of both pressure and viscosity? This is the rate of transfer of momentum due to vibrating particles. Okay, the same things actually are responsible for this Q. You have particles which are vibrating at a higher vibrational speed and frequency, basically have higher temperature, and you have particles which are vibrating at a lower frequency have, or lower amplitudes, basically have smaller temperature. How does the information of this high temperature and low temperature propagate? It is through their transfer of momentum to other particles. If you had a vacuum between them, they would never communicate, there won't be any temperature transfer. Okay, so the physical mechanism which is resulting in this surface traction is actually the same as physical mechanism which is resulting in this Q vector, and that is the momentum transfer or the rate of momentum transfer due to the vibration of molecules. So defining Q is also a part of what we called as constitutive modeling. Defining Q is also a part of constitutive modeling, just like defining T was. Okay, we gave a lot of focus on T, how to derive T, how to define T. We're not going to bother too much about Q, just going to give you the end result, and that is Q is minus K gradient of T. This is the definition according to what is known as the Fourier's law. Okay, that Q is this, where K is called the thermal conduction coefficient, it is always positive. So Q is always opposite to the temperature gradient. So if a temperature is lower here, higher here, then temperature gradient is oriented in this way, and then Q is oriented opposite to this. Okay, so Q is always minus K grad T for us in this course. Yeah. The task of defining Q is same as task of defining T. That is, how do you uh, how do you uh, how do you propagate the information from molecules to macroscopic variables? The random vibration or thermal vibration of molecules, how do you propagate that information? How do you account for that physics at the larger scales? Okay, technically everything, again, you can derive this Q from a molecular dynamic simulation, let us say. Okay, in a molecular dynamic simulation where you are not doing anything on the molecules except for solving F equals ma, you can derive what this Q is going to be, and you can derive what this T is going to be. Okay, so there are statistical mechanical tools which can help you derive this Q and T from the information of molecules, how they are moving in all liquids, gases or solids. Okay, so that is what I mean when I say defining Q is same as defining T. The task of doing this is basically constitutive modeling. Okay. And this EI, so I am not going to go into the depths of what is the specific heat capacity, what is it at constant pressure, constant volume. I am going to expect that you recall it from your basic thermodynamics courses. In a general case, I am going to define this EI as some Tref to T. In this course, we are not going to entertain any variations in Cv due to temperature, and we are only going to consider EI as this Cv times T. Okay. For us, the internal energy is going to be Cv times T, where this is specific heat capacity at constant volume. Okay, joule per kg Kelvin. These are the units. So now substituting these in our energy equation, total energy equation, we are going to get, let's say, EI plus U square by 2 plus del dot of rho U EI plus U square by 2 equals del dot K grad T plus some S dot plus some, actually I forgot F dot U here, right, plus F dot U plus del dot T dot U. Now what I am going to do is I am going to subtract kinetic energy equation from this. I am going to subtract kinetic energy equation from this. So the left hand side, you can imagine, you can easily work it out that it is going to be del by del T of rho EI plus del dot of rho U EI equals del dot of K grad T. This term will cancel out, F dot U will cancel out, right, and one of the terms from this will cancel out, and eventually you will be left with now on the left hand side. I can again play that trick of subtracting a 0 which is del rho by del T plus del dot rho U and multiply the 0 with EI. Okay, I can always do that, and the reason to do that is to bring rho and rho U out. Okay, and so the left hand side will become rho times del EI by del T plus U dot grad of EI equals del dot K grad T plus S dot plus. Now let us substitute the expression for T as well, okay, just to get the full equation, and EI as CVT, and I am going to assume, as I said, CV is constant. Throughout this course we are going to take CV as constant. So we will get rho CV material derivative of temperature equals del dot K grad T plus S dot plus, now we have T double dot grad U, which is T double dot S. What was the definition of T? So what does T double dot S simplify to? So it's a quiz question, right? So we have, this is Tij times Sij, this is minus P delta Ij plus 2 mu Sij and minus 2 mu by 3 del dot U delta Ij. So this times Sij. So this gives us minus P Sii minus 2 mu by 3 del dot U times Sii plus 2 mu Sij. What is Sii? Sii. This is not delta ii, this is Sii. S was the symmetric part of velocity gradient. So Sii is simply divergence of velocity, right? It is the trace of that. So it is minus P del dot U, and then we have this plus 2 mu Sij minus 2 mu by 3 del dot U Sii. Okay, you can look at the quiz solutions in how to completing this as a whole square. Okay, you can complete this as a whole square and show that this quantity plus P del dot U is always greater than or equal to 0, but we don't need to do that here. We just need to write this expression down for completeness, and that is this plus 2 mu Sij Sij minus 2 mu by 3. I can write this as del dot U square. So this is our temperature equation. Okay, this is what our temperature equation looks like. We derive this from the total energy equation. Okay, we derive this from the total energy equation and subtracting the kinetic energy equation from here. Notice that maybe in your thermodynamics and other classes you had a Cp here. Okay, I don't know if you guys have done those typical control volume analysis of fluid going in with some temperature, interacting with something and leaving with some other temperature, then usually you have a Cp here, but we have a Cv. We will see in the next discussion on dimensional analysis how this whole thing can be simplified under some assumptions. Okay, under some assumptions or approximations. I've given a hint of that approximation in the uploaded notes of this chapter, but we will look at the detailed derivation of those approximations in non-dimensionalization. Any questions? Any questions so far? So if there are no questions, then we can move forward with our discussion on specific to incompressible flows, because this course is mostly about incompressible flows. So you can simplify this equation for incompressible flows easily, right? This term will go away, this term will go away. Del dot U, wherever is appearing, you can substitute that to be 0 and those terms will go away. But if this is not an incompressible flow, then let me ask a question to you guys. So the all the equations that we have derived so far have been for density, velocity, temperature. Okay, we have had density, velocity and temperature. So we had 3 equations for momentum for velocity, we had 1 equation for temperature and we have 1 equation for density, but we have another variable appearing in the equations, that is pressure. Okay, so the total number of variables is 6, but the total number of conservation or governing equations that we have are 5. So there's still a missing equation, okay, and that will be your equation of state if you are solving for a gas. Okay, if you are solving for a gas, that will be your equation of state. Okay, so you will need equation of state for compressible flows, but for incompressible flows, as it turns out, we have density most of the time. In all of our examples, we are going to consider density to be constant. So if rho is equal to 1 or rho is equal to constant, let's say not 1, okay, we have velocity, we have pressure, and we have temperature. Okay, we have 5 variables and we have 5 equations. We have continuity, we have momentum, we have temperature. We don't technically need an equation of state when we are dealing with incompressible flows. Okay, so we have 5 equations, 5 variables. We have density or del dot u equals 0, which is the continuity equation or density equation, whatever you want to call it. We have the momentum equation, and we have the temperature equation. For incompressible flows, this is going to be simple, del dot. So throughout this course, we are going to again take this also as constant. K is going to be constant, just like we are taking viscosity to be constant. The thermal conduction coefficient, I am not going to entertain its variation. So it's going to be K del square T plus some S dot plus 2 mu Sij Sij. Here, if you want, you can write an F, external force. So this is the system of equations that we are going to be concerned throughout our course. Most of the times we are going to be only concerned about this system. Okay, most of the times we are going to be concerned only about the top 2 equations. Only in 1 or 2 examples we will entertain the variations in temperature. An interesting thing that you should note is the first 2 equations, or rather the first 4 equations, this is 1, this is 2, 3, 4, these 4 equations are decoupled from this one. There is no temperature appearing in these. Okay, so the temperature is not going to affect your dynamics. The flow dynamics are not affected by temperature, but the flow dynamics do affect how the temperature field gets transported. Okay, so this is, there's like a one way coupling in this system. The two way coupling is absent so far. That changes in temperature do not affect the dynamics of the flow. Again, this thing will change for just one or two of our examples, where we do have to take changes in density due to changes in temperature. Okay, we do have to account for changes in density due to changes in temperature, but other than that, there is no two-way coupling if you take density to be constant. So there are some additional derivations in the notes which I am not going to cover in class because they are rather trivial. One of them is basically how to derive your incompressible equations in a rotating frame of reference. Okay, so if this is your du by dt, this is the acceleration, then those of you who have any recollection of APL 100 will know that there will be relative acceleration terms appearing in our governing equations. Okay, so you can derive the governing equations in a rotating reference frame. That is important because most of the atmospheric flows that we are observing are on Earth, which itself is an accelerating rotating frame of reference, not an inertial frame of reference. Okay, all of these derivations so far are done in inertial frame. Any questions so far? So with this, we are going to close our discussion on derivations of governing equations, and now we will try to get into the gears of solving them. Okay, fine, you have derived these bunch of equations, who cares, how do you solve them, can we even solve them? The answer to second question is no, obviously, but not in a general case, but at least in some specific case we can solve. Okay. Some delusional people believe that AI can help us developing a theory for these equations. And these delusional people are getting Nobel prizes these days also. But yeah, so these things, I mean, even if there is a network which consumes more energy than any human being who would derive the theory, then what is the point, right? But these things are pretty hard to solve. Okay, these are non-linear partial differential equations. You cannot solve them by hand. Okay, in some cases you may be able to reduce them down into ODEs, but they will still be non-linear ODEs, and it's not very straightforward to solve those non-linear ODEs as well. Okay, so there are very few cases in which there is some solution possible by pen and paper. We are going to look at a fewer of those cases, a more subset of those cases. Okay, and I hope even that doesn't feel overwhelming to you. But this is where we stop with our deriving discussions. Okay, so it is best to take a pause, absorb whatever has gone through. Okay, if you have any questions, please ask, because from now on, this is our starting point. In most of the course, these two equations are going to be our starting points. Okay, and I'm going to assume that you know where all each of these terms have come from. Okay, so we have this, and some comments about these equations. Okay, some comments about the momentum equation, to be exact. So actually let's write both of them together, and this is del u by del t plus u dot grad u equals my. So usually this is how these equations will be represented, where I will divide the equation with rho. Okay, let's call this as f by rho, and I will divide this whole equation with rho and call this mu by rho as nu. So this quantity is mu by rho. Mu was your dynamic viscosity coefficient. This is our kinematic viscosity coefficient. Okay, where I have taken the kg out of the units basically. Okay, so you can think about this nu as mu without the effects of density. Okay, so for example, we all think that honey is denser than water. Is honey denser, more viscous than water, or both? So the answer to that question you will find if you can quantify what is rho and nu separately. Okay, you have to account for nu and rho separately to answer these questions. Okay, intuition is very hard. Intuitively, it's very hard to separate the two. Okay, some of you may jump down in your intuition and say, no, I have observed the flow of honey and I have observed the flow of water, and I know that honey is more viscous as well. Sure, you will be correct, but compare the kinematic viscosity of both, and then we can make some calls about which one is denser and more viscous. So this is a, so the second equation, this is a non-linear PDE. How do we know something is, some equation is a non-linear equation? How do we deduce that? So by inspection, you see that there is a product of two terms which consist of the unknowns. Okay, the unknown is velocity here, and you have a product of velocity. Okay, the mathematically rigorous way of showing that is you take one velocity u1, you take u2. If u1 and u2 obey the equations, then u1 plus u2 must obey the equations. Then you prove that this is a linear system, and if you do that, you will show that this is not a linear system. Okay, so this is a non-linear PDE specifically due to this term. The first term is usually called the unsteady term. Okay, so this is basically change in velocity at a given location with time. How the velocity might be changing at a given location with time. Okay, at a given location is a very important phrase here. This is called the convective term. You can call it as convective or advective term. This is change in velocity due to the transport of fluid elements. Okay, when fluid element goes from one place to another, you have a velocity field defined. How does the velocity of that fluid element change in that field? So this is u dot grad u. This is called the pressure term. This is called your viscous term, and this is called your body force term. Okay, most of the times I am going to ignore in this course body forces except for when we are taking gravity into account. Okay, so except for when we are taking gravity into account, body force term will not be present in our discussions. What is the order of this PD? The second equation, what is the order of this PD? Second order. Is just saying second order enough, or you have to specify second order in space, first order in time? Okay, basically due to this viscous term, you have a del square u, have a Laplacian of u, so you have a second order derivative in all three directions. So in each direction you need two boundary conditions to solve this equation. If your flow is three dimensional, you need 6 boundary conditions in space to solve this equation and one initial condition to solve this equation. Okay, the initial condition is because this is an unsteady flow. This is an unsteady equation. You have a del u by del t first order time derivative term. What is the main difference between a nonlinear equation and a linear equation? What is the most striking difference between the two vis-a-vis their solutions? Even in algebraic equations, let's say polynomials, what is the most striking difference between the two? Linear equations cut x-axis once, and nonlinear equations can cut the axis multiple times. So you can have multiple solutions of a nonlinear equation, but you will have one unique solution of a linear equation. Okay, so this is a nonlinear equation. There is no unique solution of a Navier-Stokes equations. Within the a given set of boundary conditions and initial condition, you can have multiple solutions. Okay, things are becoming interesting because you have multiple solutions possible. So which solutions are we going to look at? Can we look at some solutions and say these are not physically possible? Can we look at some solutions and say these may be physically possible? Okay, there are a lot of classifications possible of the solutions, but one classification which is very important for us is laminar versus turbulent flows. So for every laminar flow, for every boundary condition, set of boundary and initial conditions giving you a laminar flow, you can find a turbulent flow. Okay, the main difference between the two is that there is a turbulent flow. So the main difference is that these are unsteady inherently, unsteady. They have fluctuations at all scales. I shouldn't say all scales, at a variety of scales. Variety of scales. Okay, these can be unsteady, these can be steady as well, or steady. They don't have fluctuations, or let's call they don't have random fluctuations in the flow field. What we mean by random fluctuations is that, so there is no randomness in these equations. Okay, these are not stochastic equations. There is no random function appearing in those equations. It's just that sometimes the little details of these fluctuations are very hard to track, and as human beings we tend to model some things which are hard to track as statistical phenomena. Okay, I don't know how these fluctuations appeared, so I'm going to give them a random nature and model their probability, okay, instead of modeling them exactly. Okay, so we'll discuss more about turbulent flows later on and their fluctuations. So throughout our discussion till hydrodynamic instability, we are going to look at laminar flows. Okay, till stability, we are going to look at laminar flows. We are going to look at laminar solutions of the Navier-Stokes equations. What do these laminar turbulent solutions mean? It will become more clear as we go down in the course. Okay, I wish I could show you a visualization. Maybe next class I will show you that fluid mechanics film which does a good job of visualizing this. And it is important to note that there is no very specific definition of either of these two possible. Okay, even after, let's say, a century or more than a century of this classification, we still don't know how to define a turbulent flow. There are some characteristics or features which we can ascribe. Okay, yeah, if this is there, it's a turbulent flow, but we still don't have a very mathematically rigorous definition of a turbulent flow. So it's all visual at some point. Okay, it's all visual and it depends on your intuition at some point. So before we get into some examples where we solve these equations, let us take a note of different boundary conditions that we may encounter. Okay, let us look at different boundary conditions that we may encounter in this course. The first type of boundary conditions are wall, or rather hard wall boundary conditions. Let us say you have a fluid flow taking place and there is a wall like this. Okay, the wall has some normal n, there is fluid flow happening here. Okay, then a hard wall boundary condition basically says that the fluid velocity or velocity of the fluid at the wall is equal to the velocity of the wall. Velocity of the fluid at the wall is equal to the velocity of the wall. That is both, let's say the velocity of the wall is some v vector, then u dot n at the wall is equal to v dot n. Velocity of the fluid at the wall, not everywhere, at the wall, velocity of the fluid is equal to the velocity of the wall. This will be called no penetration boundary condition. So the hard wall boundary condition is a part of two boundary conditions. The first one is called the no penetration boundary condition. The other one is that if velocity is equal, the normal component is equal, then whatever remains is also equal. Whatever remains if you remove the normal component, the tangential component. So u minus n times u dot n at wall is equal to v minus, okay, and this is called no slip boundary condition. So the words are very self explanatory. Okay, there is no slip of the fluid on the wall. Whatever speed of the wall is tangentially, that is the speed of the fluid tangentially. Whatever speed of the wall is normally, that is the speed of the fluid normally. As we move down in the course, we will see that these two specifically the no slip boundary condition. No slip boundary condition happens due to viscosity. If you ignore viscosity, then actually it is rather impossible to satisfy a no slip boundary condition. If you satisfy no slip and you remove viscosity from your analysis, you will find that there is basically no flow. Okay. So, we will see that this no slip wall boundary condition needs viscosity to support itself. Okay. And whenever we are discussing all of this, you should keep in mind that whenever we encounter, when we go towards modeling, when we go towards inviscid flows, we will encounter this question, which boundary condition to drop. Okay. Because no, when you drop viscosity, you will see that your partial differential equation remains nonlinear, but will no longer be second order. When you drop the viscous term, the PDE will no longer be second order. So, you will have to get rid of some boundary conditions to solve the remaining equation. Which boundary conditions to get rid of? Is it ad hoc? Is it arbitrary? No. Okay. We will discuss that as well. So, these are hard wall boundary conditions. Then there are porous wall boundary conditions that we can define. So, in porous wall, so you have a porous wall. Basically, you have a wall that may have some pores through it. Okay. And then you say that there is no slip. So, no slip exists, and for the normal velocity, what we have to define is there is a the pressure difference between the two sides of the wall, and what we say is that u dot n at wall is equal to minus k by mu p1 minus p2. So, if the fluid is here, flow is happening here. So, if p1 is larger, yeah, this is how the convention is. So, p1 is on the side of fluid and n is the normal towards the fluid, then u dot n wall is equal to this, where this k is the permeability of the wall and mu is the viscous coefficient, dynamic viscosity. There are some other boundary conditions also that we will look at tomorrow in detail, and we will look at, in the most detail, we will look at the so called interface condition. That is, when you have an arbitrary interface between two fluids, let us say A and B. So, when you have an interface between two fluids, then how do the quantities match at that interface? What quantities match at that interface? What is supposed to be equal? What is supposed to have a jump in it? Okay, we will look at this tomorrow.